The outer solar system has a tilt. Not a dramatic one, 15 degrees. But that number has been eating at planetary scientists, because nothing out there should be doing it. Here's what 15 degrees actually means. The 8 known planets orbit the Sun on roughly the same plane, a flat disk inherited from the spinning cloud of gas and dust that formed the solar system 4.5 billion years ago. That plane is not a suggestion. It's a physical consequence of how angular momentum works. The debris in the outer solar system, the trans-neptunian objects, the scattered disk, the distant belt, should respect that same geometry, and for the most part, it does. Except the plane of the outer disk is warped. The population of small, icy bodies beyond Neptune is systematically tilted relative to where it should sit. 15 degrees off. Coherently, not randomly. Not the kind of scatter you'd expect from a billion years of gravitational noise. This is a structured deviation, a warp with a direction. That's the thing that demands an explanation. Random scatter produces a blur. A coherent tilt in one direction points at a source, something massive enough, and positioned correctly, to drag the orbital plane of an entire population of objects off its natural axis and hold it there. Astronomers have run the numbers on every known body in the solar system. Neptune can't do it. Its gravity is already accounted for in the baseline. The known dwarf planets are too small. There is no combination of catalogued objects that produces a warp this clean, this large, this persistent. Which leaves one possibility nobody wanted to write down until the math forced it. Something unknown is out there, something with enough mass to sculpt the outer solar system from a distance. And a team at Princeton thinks they know what it is. The Princeton team didn't start with a planet. They started with a residual, a signal left over after everything known was subtracted out. Strip away Neptune, the giant planets, every catalogued dwarf object, and what remains is a gravitational fingerprint that doesn't belong to anything on the books. So they work backward from the warp to whatever object could plausibly produce it. The math constrains the answer tightly. To generate a 15-degree tilt across the orbital plane of that many outer bodies, consistently, the responsible object needs to sit somewhere between 80 and 200 astronomical units from the Sun. For reference, Neptune orbits at about 30. This thing is 2 to 6 times farther out than the most distant known planet, sitting in a region we've barely mapped. The mass range is where it gets specific. The signal is too strong to come from a small body, but it doesn't carry the signature of something gas giant-sized. Run the orbital mechanics and you land between 1 and 3 Earth masses, the range occupied by rocky terrestrial planets. Mercury at one end of the comparison, Earth at the other. Not a failed gas giant, not an ice giant like Uranus or Neptune. Something dense and rocky, sitting in the dark at the edge of the solar system. That distinction matters more than it sounds. Gas giant hypotheses are easy to generate. Big objects at extreme distances have been proposed before. What's unusual here is the precision of the constraint. The warp doesn't permit a vague answer. It points to a specific mass bracket, a specific distance range, a body that would look, physically, like an inner solar system planet stranded impossibly far from where it has any right to be. Which raises the question the Princeton team can't yet answer. How did a rocky terrestrial body end up out there? And that question splits into 2 very different possibilities, each with its own consequences for everything we thought we knew about how this solar system was built. Before this goes any further, there's a conflation that needs to be killed. Because the moment most people hear unknown planet in the outer solar system, one name surfaces: Planet 9. And Planet Y is not Planet 9. They are not the same hypothesis, not the same evidence, not even the same region of space. Treating them as interchangeable is the kind of shortcut that makes both harder to understand. Planet 9 has been on the table since 2016, when Caltech researchers Batygin and Brown noticed that a cluster of distant trans-neptunian objects, small, icy bodies in the outer solar system, seemed to have their orbits bunched together in a way that looks statistically unlikely without something massive shepherding them. Their candidate, a gas giant, somewhere between 5 and 10 times Earth's mass, orbiting at roughly 400 to 800 astronomical units from the Sun. Far out. Massive. A true giant. Planet Y is none of those things. It sits between 80 and 200 astronomical units from the Sun. Far out. Massive. A true giant. Planet Y is none of those things. It sits between 80 and 200 astronomical units closer in by a significant margin. Its inferred mass is Mercury to Earth range, not a giant by any definition, rocky rather than gaseous. And the signal driving it isn't the clustering of small icy bodies. It's the 15-degree tilt of the solar system's invariable plane itself. A different dataset, a different measurement, a different anomaly entirely. Two separate researchers, looking at two separate features of the outer solar system, using two separate methods, arrived at two separate candidates. That's not redundancy. If anything, it's more unsettling, because it suggests the outer solar system may be hiding more than one surprise. Planet Y doesn't explain the clustering that motivated Planet 9. Planet 9 doesn't explain the warp that motivated Planet Y. They may both be real. They may both be wrong. But they are not the same argument wearing different clothes. So assume for a moment that Planet Y is real. The next question isn't where it is, it's where it came from. And the two answers on the table couldn't point in more different directions. The first scenario, Planet Y formed somewhere else entirely, and the solar system stole it. In the early chaos of the galaxy's stellar nursery, young solar systems passed close enough to each other that gravitational exchanges were possible, probable even. A small rocky body on the outer edge of a neighboring system could have been stripped away and captured into a wide, tilted orbit around our sun. That's not speculation dressed up as science. We have strong evidence that the solar system captured at least some of its small outer bodies this way. The question is whether something large enough to warp the invariable plane came along for the ride. If it did, Planet Y would be an alien world in the most literal sense, a rock that formed around a different star, under different conditions, and has been drifting through our outer solar system ever since, undetected, tilting the plane of everything that came after it. That should unsettle you a little. The second scenario is quieter, but in some ways stranger. Planet Y formed here, in our own protoplanetary disk, and simply never left. Standard models of solar system formation have always struggled to account for everything cleanly. There are regions of the disk where conditions could plausibly grow a rocky body to Mercury or Earth mass and then leave it stranded far out, on an eccentric orbit, after the giant planets reshuffled everything in the early solar system's violent youth. In situ formation means Planet Y has always been ours. It would be the most distant native planet, a sibling we somehow missed for 4.5 billion years. Each scenario rewrites something. A captured rogue rewrites our solar system's relationship with the galaxy. We are not as isolated as we assumed. In situ formation rewrites our models of how planets survive and where they end up. The warp is the same either way. What it means depends entirely on which origin is true, and right now, neither can be ruled out. So we have two scenarios, one warp and no way yet to choose between them. That changes with a telescope that just came online in the Chilean Andes. The Vera C. Rubin Observatory sits at 9,500 feet on Cerro Pachón, and it is not like anything that came before it. Its primary mirror spans 8.5 meters. Its camera, the largest digital camera ever built for astronomy, captures 320 megapixels per frame, covering a patch of sky roughly 40 times the area of the full moon in a single exposure. Every 3 nights, it will photograph the entire southern sky. Then it will do it again, for 10 years. That cadence is what makes it the right instrument for this search. Planet Y, if it exists, is not going to announce itself with a single bright flash. It will show up as a faint, slow-moving point, drifting against the background stars over months and years, dim enough that every previous wide-field survey missed it entirely. What Rubin does is accumulate, each image stacked on the last, building a time-lapse of the outer solar system precise enough to catch something moving at roughly 80 to 200 astronomical units out. The search is already being designed around the warp signature itself. The Princeton team's orbital model constrains where Planet Y should be in the sky, not a pinpoint, but a probability corridor. Rubin will scan that corridor repeatedly, flagging anything that moves on the right trajectory, at the right speed, at the right distance. If Planet Y is there, it will leave tracks in Rubin's data within the decade. If Rubin runs its full survey and the corridor stays empty, the warp needs a different explanation, and the candidate quietly disappears. Either answer is a verdict, and for the first time, we actually have the instrument to deliver one. So let's say Rubin finds it. Let's say a point of light moves through the probability corridor on exactly the right arc, and the orbital math locks in. What actually changes? Start with the architecture, the standard model of solar system formation, the one written across every textbook printed in the last 30 years, holds that the outer solar system is largely settled. The giant planets carved their lanes early, scattered the debris into belts and clouds, and the geometry stabilized. A rocky world sitting between 80 and 200 astronomical units, massive enough to warp the plane of the entire outer disk, doesn't fit that picture. It breaks it. Because an object that size doesn't just sit there quietly. It perturbs. It nudges long-period comets onto trajectories they wouldn't otherwise take. It shapes the Kuiper Belt's edge in ways we may have already measured without understanding why. Every orbital survey we've run on the outer solar system, every unexplained clustering, every anomalous inclination, gets re-examined the moment a new gravitational source enters the model. Some of those anomalies may resolve, others might deepen, but here is the beat worth sitting with. The in situ formation scenario, planet Y born from this solar system's own disk, is strange enough. It demands that something rocky and massive survived in the deep outer solar system while everything nearby was scattered or consumed. The captured rogue scenario is stranger still. It means our sun, at some point in its early life, reached out gravitationally and held onto a world that formed somewhere else entirely, around another star, or in the void between them. A planet that never belonged here. A world with no birth certificate in this solar system, orbiting our sun for billions of years, completely unknown to us until a 15-degree tilt in a distant disk gave it away. We would be sharing a solar system with an interloper, not a visitor, a permanent resident. And we had no idea. That's the position we're in right now. Not knowing. A world that may have orbited our sun for billions of years, close enough that its gravity bent the shape of the outer solar system, and we only noticed because a disk of distant ice was tilted 15 degrees in the wrong direction. There's something clarifying about that. We talk about the solar system as a known quantity. 8 planets, cataloged, named, textbook diagrams printed for a century. And yet the census was never finished. It was just paused at the edge of what we could see. The outer solar system is not empty. It is dark. Those two things are not the same, and the distinction matters enormously. Every instrument we've pointed outward has been limited by light, by time, by the sheer scale of what's out there. Planet Y, if it exists, didn't evade detection through luck. It evaded detection because we didn't have tools capable of finding it until now. The Rubin Observatory changes that. Within a decade, the map either gains a new world or the anomaly finds a different explanation. Either outcome is a kind of knowledge we don't currently have. What the Princeton result really asks is a harder question than is there another planet. It asks how confident we should be in any map drawn at the edge of our instruments. The answer, apparently, is less confident than we thought. The solar system census is still open. The next decade will close it a little further. And somewhere between 80 and 200 astronomical units from the sun, something is either out there or isn't. We're about to find out which.